Welcome everyone. This is MCLinker, the final toolchain frontier talk. I'm Joerg Sonnenberger, welcome. I hate this microphone. So a small overview over the presentation. I'm going to give an introduction to what MCLinker is about. I'm going to talk about the architecture of the linker, the performance seen on NetBSD. I'm going to go into some details of how well it works on different systems, and I'm going to talk about what's left to do. So what's MCLinker? Basically, it stands for Machine Code Linker, and it complements the Machine Code layer in LLVM. It was created by Lubateng from MediaTek just 2 years ago. And what makes it very attractive for NetBSD is that it's using the same license as LLVM itself. So it will help us to get rid of one of the final pieces of GPL3 code in the toolchain.
Are you using LLVM in NetBSD?
So the question is, are we using LLVM in NetBSD? Not yet in the main tree. There's basically all the infrastructure is around. You just have to set two flags and check out the repositories using Subversion. It is fully integrated. We support x86 at the moment as platform, simply because I haven't had that much time to work on the other platforms yet. So the high-level view of the architecture is MCLinker is building an intermediate representation of the input, called the input tree. From that, it builds a fragment reference graph. Then it's going to lay out the sections, do some fancy magic with relocations, and then it's going to write the output. What's interesting here is that the new LD doesn't have any clear design like this. Basically, it's doing all these three operations kind of in a tight loop, adding things as it needs to. And that's one of the reasons why it's relatively slow and relatively complicated in terms of code. Code Google's linker is much cleaner. It still has the first two parts merged together, which is still somewhat unclear, but it's much better in terms of architecture. So when we build the input tree, the goal is to have a high-level description of what the user wants us to do. So basically, this takes the command line and applies whatever knowledge is necessary from the file system. So basically, if the command line says, okay, I want to link against libc, this is the phase where it decides what libc we actually want to look at. And we have to deal with positional arguments here. For example, start group or as needed apply to the next files or libraries, and they can be disabled again. And so this the tree has to include a representation of that. the tree has to support nesting because linker archives can contain other objects. And there are different types of objects we are dealing with. There are plain object files, there are linker archives, there are shared libraries. And there are different semantics as far as linking is concerned for each of those. Once we have the input tree, we want to build the fragments reference graph. What is basically going on is that we want to resolve the symbols found in the different object files. And so we built a graph where each section in one of the object files we are dealing with is a node, and every symbol reference is an edge. So the problem basically becomes finding the necessary spanning part of the graph to create the output. So what it does is it traverses the input tree and looks for files. Most importantly, of course, object files, but linker archives, for example, have similar behavior. It's important to check whether this file was either requested by the user or it provides some symbol definition we are currently missing. So in either case, we want to include this for the further processing. Shared libraries are only kept as reference. So a symbol defined by a shared library still stays undefined, but we know about it, so we can continue. For the linker archive, we want to pull in the corresponding part of the archive. If we are interested in this file, we actually open it and read the sections and the symbol tables. Linker groups require a bit more magic. In this case, we have a stack, and whenever we hit the start of a linker group command, we push the current position in the input tree onto the stack, and we continue processing inside this group as long as there are still some undefined references that have been added in the iteration. Consider, for example, static linking against libc. We have like printf as undefined symbol from our object files. Printf needs write, so when we open printf.o, we see the missing reference to write. So we also have to pull in whatever object file provides write. So this loop continues until no new undefined references are found. The reason to do this very carefully and in this order is we want to provide as much cache locality as possible. So the data structures involved here are carefully designed. So, for example, the representation of a symbol contains all the important attributes and the initial part of the name. That's basically what we care about most often. So that's what we want to keep in a single cache line on a modern CPU. It's not really important what some ancient stuff is doing here. We care mostly about the systems people develop on. And so you want to stay within 16 or 32 bytes for the really hot data, because that's what your CPU is optimized for. once we have all the sections determined, we are going to pick up. We want to decide which order they should appear in the output file and at which position. So the layout phase basically merges sections that have the same name, like two object files providing the text section. But we also merge subsections. For example, in C++, we often have inline definitions where the section name contains the name of the class and the method provided, and you want to merge those into the larger text segment. This part also has to decide what input sections are no longer needed. For example, because they are not referenced, or because there are multiple definitions that are equal, and where only one of them should be picked up. And ultimately, in this phase, we also decide what the values of the individual symbols are. So the symbol value could be an absolute address, it could be relative to the start of a segment, or it could just be undefined ODP. Doing layout as a separate phase after building the complete input tree has a really big advantage that we only have to do all this computation once. So we do a single pass over all the segments and all the symbols, and that saves a lot of time and also avoids trashing caches earlier. So now that we know where every chunk of code is going to appear at, we can apply our knowledge of the symbol values and adjust relocations as necessary. A relocation basically says I want to use the difference between my current position and this symbol, or I need the position of this symbol at this place. And if we're doing static linking, we can write all the positions down because all the symbols are known, nothing changes at runtime. So all these relocations are going to be eliminated because they are fixed. Well, it's a bit more complicated if we're doing dynamic linking, because in that case we still have references to shared libraries. So we have to decide which of those are still kept. And sometimes we can replace them with cheaper versions. For example, if we have a hidden symbol in a library, that means the symbol can only be used inside this library. We can replace all relocations that reference a symbol with a relocation that just depends on the final position of our object in the memory image. It doesn't need to actually look at the symbol and do a name lookup. It just has to adjust for the position in virtual memory.
I'm just waiting.
Yeah. There are some important considerations here for architectures like ARM or MIPS. They can only encode immediate values of a certain range. For ARM, for example, you can include 24-bit inside a jump or call instruction. So if you want to have if you want to reference an address that is larger than 24-bit, you have to save it to a memory location and use a load instruction from that. So the linker can sometimes optimize those and pull those out. Another example of an optimization is thread local storage. If you know this is going to be the main binary, you can remove most of the really expensive access code and just wire it down as much as possible. But the last part of linking is writing the final binary. So we take the relocations we've computed in the phase before, and we take the input sections we found while building the Fragments reference tree and combine that and write it to the binary. We have to add some metadata, for example, all the elf wrapping around. That's also done. And at the end we have a binary. MCLinker is very aggressive about using memory mapped files. There are three reasons for doing that. The first, of course, is it helps the CPU to use the PLD cache as much as possible. It also helps to keep the data hot in the cache if you have a medium-sized input. And finally, it helps the operating system to use its own cache as efficient as possible. So all this hard work is done. Let's see how does it perform. There are three linkers I'm going to compare. That's GNU-LD, that's Google Gold, and of course MCLinker. And I'm looking at two larger binaries, which is the TableGen helper program from LLVM, and that's Clang itself. Both cases are mostly static binaries, so they still link against libc, but all the LLVM libraries are linked in statically, so the linker actually has to do quite a bit of work here. If you compare the runtime, it's easy to see that GNU-LD is taking at least twice as long as both Gold and MCLinker. Gold is still a bit faster than MCLinker, so there's some careful profiling going to be needed in the future. But it's not that bad. What's interesting is the memory usage. GNU-LD clearly has some advantage here when it comes to linking the Clang binary, because it doesn't keep all the input in memory, like all the full symbol table all the time. It can forget about symbols earlier. The price of that is, of course, that it takes quite a bit longer to link. And the second important part when talking about the performance of a linker is what's the size of the resulting binaries. It should be obvious that the text segment currently is quite a bit larger for MCLinker compared to both Gold and GNU-LD. On the other hand, data and initialized memory sections are often smaller. There's a copy and paste error here. That number is wrong. So what happens here? The first part is MCLinker currently still works like export dynamic is provided. So the dynamic symbol table is much larger than both GNU-LD and Gold. And if you look at the at the text size in detail, that's one major part for Clang that accounts for 2 megabytes of the difference. And the other part is the size of the read-only data section. MCLinker currently does not laminate redundant string storage. So if you have two identical strings somewhere in anonymous memory locations, both NuLD and Gold will store only one copy in the final executable. MCLinker doesn't do that yet. I think that's most of the rest. If you look at the actual code size, MCLinker is actually better than both NuLD and Gold. So what's the implementation status? That can be divided into platform-independent parts and platform-specific parts. In the platform-independent area, most of the basic functionality just works. So we have static and dynamic linking, we have partial linking, that is LD-R. We have the visibility and binding rules, all of those is implemented. One part that's missing is if you have a shared library that links against other shared libraries. Elf rules says all the symbols visible from those dependent libraries are also visible from the original library. And that part is not implemented in MCLinker yet. Amusingly, the binutils folks recently decided to screw that part of ELF behavior and require you to link against every single library explicitly. So modern NuLD is as bad as MCLinker in this regard now. But this is considered a bug for MCLinker, so it's going to be fixed at some point. If you look at x86, I have all the parts for NetBSD release building done. There are a few areas where I still have to fall back to NuLD because there's no linkers with support yet. That's actively worked on. And there are a few test cases from the ATF regression test suite that are failing because TLS support is a bit incomplete. The relaxations to cheaper access models I was talking about earlier isn't done yet completely. One area that changed compared to the printed version is the status for ARM. I spent the last 2 days working on that, so basically release building works now. I have a few more hacks in it than x86. The most important hack is that an optimized libc doesn't work yet. The only dynamically linked program that didn't crash immediately was cat. Give me a bit more time. I hope to have it figured out pretty soon. So TLS support is also incomplete, just like x86. There are a few nasty hacks needed to get the ELF header flagged correctly. This is mostly an issue for interoperability with NuLD, because NuLD wants to have the ABI tagging with the ARM-specific flags in every object file, otherwise it's just going to punt. And I'm not sure how we are going to integrate that in a clean way. On the other hand, on ARM, it's an optional system linker for Android, both for cross-compiling and for running on the target system. And one limitation is there's currently no support for 64-bit ARM. Well, given that no one outside a certain few special ARM vendors has this hardware, this is not such a big limitation. There's also quite a bit of support for MIPS. On Android, it has the same status as ARM, but I didn't have time to play with it for NetBSD yet. The support for the 64-bit ABIs doesn't exist yet, so it's going to take a bit more work. Well, what's left for the future? What we definitely need to work on is building an extensive test suite. There are quite a few areas where it's still too easy to hit an assertion because something is not implemented completely or correctly, and it would be very nice to exercise all those parts nicely. Symbol versioning is currently missing. This doesn't matter that much for NetBSD because the only library that actually uses symbol versioning is libgcc. I think it's going to be much more critical for FreeBSD. I mentioned them already. Linker scripts are missing. For NetBSD, that means main kernel and rump. Link time optimizations are not supported either. For LLVM, that shouldn't be that difficult to fix, but no one cared yet enough. There's a research question of adding fine-grained layout. How does it affect code size and performance if you do the linking step basically on a per function base? There are a few optimizations missing for the exception tables. To be fair, that's something the other linkers are also not necessarily very good at. First time I tried to debug exception handling, I was really surprised by viciously bogus records created by GNU-LD. So everyone can take some work here. And well, for the platforms, there are the few missing items for x86, ARM, and MIPS to be done. There's work in progress code for the 32-bit AMD64 ABI from the GNU forks. There's work on the 64-bit support for MIPS. The Hexagon platform is also not complete yet, but started to appear in the repository. And of course, other platforms like 64-bit ARM are not started yet, but would be very welcome. Some references, the MCLinker main repository, the bug tracker, and the homepage is on Google Code. There is a very nice tutorial from the CGO workshop a few weeks ago, which goes into a lot more of the implementation details. So if you're interested in that, check it out. And last but not least, I would like to mention a number of companies that have either donated money or experience or plain developer time. MediaTek, of course, is the original and main contributor. Google, Intel, Linux, and Qualcomm all have different degrees of contributions, and the current state wouldn't be possible without them. So, are there any questions left?
I have a simple question.
Yes.
What does the MC stand for?
Machine code.
Machine. Oh, right. Okay, you said it.
Yes.
Yeah, okay, fine. And how many active developers are contributing?
Good question. I'd say there are maybe half a dozen regular contributors, and I think it's maybe a dozen or so that have commit access to the main repository at the moment. So it's relatively small if you compare it, for example, to LLVM itself. But it's also quite a young project, so it's not that surprising.
And is this part of a bigger goal? I mean, is the idea you want to have completely GNU-free toolchain?
Certainly.
Okay.
I mean, if you look at what parts of the toolchain you need, we have pretty well working compiler for C and C++ now, so that's done. We have almost complete support for assembling, at least on x86 and new ARM. There are some areas in the, especially when it comes to the boot process on x86, that still need to fall back to the GNU assembler. But those are fixable. And the last part of GNU tools that couldn't be replaced easily, or at least with a manageable amount of development time, was Linker. And it's mostly at the point now where it's fine-tuning the code, and the big parts, except the linker scripts, are done. So I really hope in the next year that NetBSD can be built without any new dependency, at least for the modern architectures. Other questions? Well, in that case, thanks for your attention.